There is a liquid on this earth that climbs out of its container. You pour it into a cup. You set the cup down. You watch carefully. And the liquid, very slowly, very deliberately, walks up the inside wall, crosses the rim, comes down the outside, and forms a drop at the bottom. The drop falls. Another one forms. Another one falls. The liquid is escaping by itself. Nobody is shaking the cup. Nobody is heating it. Nobody is reaching in and pulling. The thing is climbing out under its own power. Before you tell me this is impossible, let me tell you something else about it. The liquid in question is colder than anything you have ever touched. Colder than dry ice. Colder than liquid nitrogen. Colder, actually, than outer space. It is so cold that the cosmic background radiation, the leftover heat of the universe itself, would feel like a blowtorch next to it. We are talking about a substance that exists only a few thousandths of a degree above absolute zero. The substance is helium-3, the lightest, rarest isotope of the second lightest element on the periodic table. And what it does when you cool it down far enough makes no sense. Not by the rules of any liquid you have ever met. So today, you and I are going to be detectives. We have a crime scene. The crime is the violation of common sense by a liquid. The suspect is helium-3. We will follow the clues, one by one, and we will not let anything off the hook until it confesses what is really going on. Bring your skepticism. Bring your patience. We are going to need both. Let's start with what we know about ordinary liquids. A liquid is supposed to sit there. That's what liquids do. You pour water into a glass, the water sits in the glass. It does not climb up the walls and run off down the outside. Why doesn't it? Well, gravity is pulling it down. The water sticks to the glass a little bit, by something we call surface tension and adhesion, and you can see this if you look closely at the meniscus, the little curved lip where the water meets the glass. The water actually does try to climb the wall a tiny amount. Look carefully, and you will see it. The edge curls upward, just a hair. But it stops there. It does not keep climbing. Why? Because the water has weight. It has internal friction, what we call viscosity. And the energy required to lift a column of water up the wall is more than gravity will let you have for free. The water climbs the tiniest fraction of a millimeter, hits a balance, and sits. That is what every liquid in your kitchen does. Olive oil, vinegar, coffee, beer, honey more slowly, but still. They all behave themselves. The meniscus exists because the molecules at the edge are slightly attracted to the glass. But the bulk of the liquid stays put. That is the law of liquids in a gravitational field that has friction in it. And it is a very reliable law. You have never seen anyone's morning tea evacuate the mug by itself. Now I show you helium-3. I cool it down. I pour it into a beaker. And it climbs all the way up the wall, all the way over the top, and all the way back down the outside. The cup empties without any help. What broke? Here is your first clue. Temperature. You cannot do this experiment at room temperature. You cannot do it in a freezer. You cannot do it in a vat of liquid nitrogen, which is already at minus 196 degrees Celsius. That is cold. Much colder than a winter day in Antarctica. Much colder than the dark side of the moon. But it is not cold enough. You cannot even do it in a container of regular liquid helium, helium-4, the kind we use for cooling powerful magnets. Liquid helium-4 boils at about minus 269 degrees Celsius. That is only 4 degrees above absolute zero. To put that in perspective, at 4 degrees above absolute zero, almost everything in the universe has frozen solid. The air, if it were there, would be solid. Hydrogen, the most fluid gas in the universe, would be a slab of ice. Mercury, alcohol, nitrogen, oxygen, every common substance is locked rigid. The only thing still liquid at 4 degrees above absolute zero is helium itself. But 4 degrees is still not cold enough. To see helium-3 climb walls, you have to go 1,000 times colder. About 2/1000ths of a degree above absolute zero, 2 millikelvin. Let me dwell on that for a moment, because the number is hard to grasp. To make helium-3 do this trick, you need a piece of equipment, in my lifetime built only in a few laboratories on the planet, called a dilution refrigerator. It is a beautiful Baroque machine. It works by mixing helium-3 and helium-4 together and pulling them apart in clever stages, using the heat absorbed by the mixing process the way an air conditioner uses evaporating coolant, but pushed to absurd extremes. It is, in essence, a refrigerator inside a refrigerator inside a refrigerator inside a refrigerator. Each stage gets a little bit colder than the last. The final stage, called the mixing chamber, can reach down into the millikelvin range. Below that, special tricks are needed. The temperature it produces is, in a real sense, the coldest temperature in the universe that we know of. The cold of empty space, the cosmic background, sits at about 2.5 degrees above absolute zero, 1,000 times warmer than what's inside that mixing chamber. There is no natural place, anywhere we have looked, that is as cold as the inside of a working dilution refrigerator on Earth. We humans, with our clever steel and clever helium, have made a colder spot than the universe has ever made on its own. So clue number 1, temperature matters. Whatever helium-3 is doing, it only does it when the temperature is unimaginably low, when everything else has thoroughly frozen and gone quiet, when the atoms have almost no thermal motion left at all. That tells us something, but not enough. Cold things are usually boring. Cold things sit still. Cold things become more orderly, more crystalline, more solid. A glass of water put in the freezer becomes ice. Ice does not climb out of the glass. It just sits there. Helium-3, when cooled, does the opposite of getting boring. It becomes more lively, more mobile, more mischievous. That is suspicious. Whatever is in our suspect, the cold is not putting it to sleep. The cold is waking it up. Let's pick up clue number 2. The difference between helium-3 and its close cousin, helium-4. You may not know this, but the helium in a balloon at a birthday party is not all one thing. There are 2 kinds of helium atoms in nature. The common one is helium-4. It has 2 protons, 2 neutrons, and 2 electrons. Almost every helium atom you ever meet is this kind. Maybe 99.999% of them. The other kind, helium-3, has 2 protons, only 1 neutron, and 2 electrons. It is much, much rarer. You can pull tiny amounts of it out of natural gas, or you can produce it through certain nuclear reactions. But you do not bump into it casually walking around. For most purposes, an atom is an atom. If I gave you a flask of helium-3 and a flask of helium-4 and asked you to tell them apart by chemistry, you couldn't. They have the same number of electrons. They form the same bonds, or rather the same lack of bonds, since helium is a noble gas and doesn't bond with much. They are chemically identical twins. But underneath, in the deep machinery of quantum mechanics, they are not the same at all. They are profoundly different. They are, in fact, opposite kinds of beasts. This is going to take a minute, so stay with me, because this is the heart of the mystery. Every fundamental particle in the universe falls into one of 2 camps. We call them fermions and bosons. The names don't matter. What matters is the rule each of them follows. A fermion is an antisocial particle. It cannot occupy the same state as another fermion of its kind. If one fermion is sitting in a particular place, doing a particular thing, no other fermion of the same type is allowed to sit in that exact place doing that exact thing. We call this rule the Pauli exclusion principle. And it is the reason atoms have shells, the reason chemistry exists, the reason matter takes up space at all. Electrons are fermions. Protons are fermions. Neutrons are fermions. The whole structure of ordinary matter is built on this rule of antisocial fermions refusing to share their seats. Picture a stadium where every fermion has assigned seating. And every seat is unique, and no 2 fermions are allowed in the same seat ever, even briefly. That is the world of fermions. Crowded, structured, full of rules. A boson is the opposite. A boson is friendly. A boson loves to be in the same state as another boson. The more bosons you put together, the more they want to pile into the same configuration. Photons, the particles of light, are bosons. That is why you can have a laser where countless photons all march in lockstep, doing the exact same thing at the exact same wavelength. Try to make a laser out of electrons, and you fail, because the electrons would refuse to all be in the same state. Picture instead a dance floor where everyone wants to do the same dance step at the same moment. And they prefer it that way, and the more people doing the step, the better the dance feels. That is the world of bosons. Cooperative, coordinated, eager to share. Now here is the question. Is a helium atom a fermion or a boson? The answer, it turns out, depends on which helium we are talking about. Helium-4 has 2 protons, 2 neutrons, and 2 electrons. 6 fermions total, all bound up tightly into one little package. When you stick 6 fermions together into a single tightly bound bundle, the bundle as a whole behaves like a boson. The fermionness of each piece cancels out in pairs. So a helium-4 atom is, to good approximation, a boson. Friendly, wants to be with its neighbors, wants to share a state. Helium-3 has 2 protons, 1 neutron, and 2 electrons. 5 fermions. Odd number. When you stick 5 fermions together into a tightly bound bundle, the bundle as a whole behaves like a fermion. So a helium-3 atom is a fermion. Antisocial, refuses to share, insists on being a unique snowflake. Same chemistry, opposite quantum statistics. This is clue number 2, and it is enormous, because it means the 2 heliums should behave completely differently when you cool them down to nothing. When you cool helium-4 down to about 2 degrees above absolute zero, something extraordinary happens. The helium-4 atoms, being bosons, do what bosons love to do. They start piling into the same quantum state. A huge fraction of them, billions and billions, all settle into a single shared configuration. The liquid stops being a collection of individual atoms doing individual things. It becomes one giant coherent thing, like one note played on a cosmic instrument. We call this a superfluid. A superfluid has no viscosity. 0. It has no internal friction. It can flow through a tiny hole that an ordinary liquid would never get through. It can swirl in a cup forever, without slowing down. And yes, it climbs walls. This is the famous experiment from the 1930s. Pyotr Kapitsa, in Moscow, and John Allen and Don Misner in Cambridge discovered almost simultaneously that helium-4 below a certain temperature does these impossible things. Bernard Rollin discovered the climbing the walls effect in the same era, and we now call that thin invading layer of superfluid the Rollin film. So you might think, aha, the mystery is solved. Helium-3 climbs walls because it is a superfluid. Same as helium-4. Case closed. Pack up. Go home. That would be a good guess. But it is wrong. This is where it gets interesting. Because helium-3 is a fermion, and fermions are not allowed to do what helium-4 atoms do. A fermion cannot pile into a shared state with all its friends. The Pauli exclusion principle forbids it. If 1,000,000 helium-3 atoms tried to all settle into the same quantum configuration, the universe would say no, you are not allowed. So when we cool helium-3 down to those 2 degrees above absolute zero, where helium-4 has already become a superfluid, helium-3 just sits there. Cold, liquid, boring. It does not climb walls. It does not flow through tiny holes. It is, despite the cold, a perfectly normal liquid. A polite, well-behaved cold liquid that obeys gravity. This was puzzling for a long time. People knew helium-3 was a fermion. They knew it could not become a boson superfluid by the simple bosonic mechanism. They expected then that it would never become a superfluid at all. And for a long time, when they looked, they saw nothing. A normal cold liquid, refusing to do tricks. Yet here we are, decades later, and I am telling you that helium-3 climbs out of the cup. So something else is going on. Some second mechanism. Some quieter mechanism. a trick that needs more cold and more patience. Here is your third clue. The temperature of the helium-4 superfluid transition is around 2 degrees above absolute zero. The temperature of the helium-3 superfluid transition is around 0.02 of a degree above absolute zero, a factor of 1,000 colder. Whatever helium-3 is doing, it requires 1,000 times less energy to disrupt than what helium-4 is doing. It is much, much more delicate, much more fragile, much weaker. The slightest amount of thermal jiggling will destroy it. You have to go 1,000 times colder than the helium-4 case to even let the effect take hold. Think about that. We have a fermion, which is not allowed to do the bosonic trick. But somehow, at obscenely low temperatures, it does start doing tricks. It climbs walls. It flows without friction. It conspires. The answer to this puzzle, when we finally got it, was the most beautiful kind of answer in physics. Beautiful because it had already been worked out, in a different context, before anyone realized it would solve helium-3. Let me tell you about the other context first. You know what a superconductor is. You take a metal, like lead or mercury or tin, and you cool it down to a few degrees above absolute zero, and suddenly its electrical resistance disappears. Drops to zero. Electrons flow through the metal without losing any energy. You can set up a current in a loop of superconducting wire, walk away, come back a year later, and the current is still flowing exactly as it was. No friction, no loss, a persistent quantum current that just goes and goes. This is strange, because electrons are fermions. They should not be able to do this collective superflow trick, for the same reason helium-3 atoms shouldn't. The Pauli exclusion principle stands in the way. Electrons cannot all settle into the same state. They are antisocial. They have assigned seats, yet they do something equivalent. And the way they do it, worked out by John Bardeen, Leon Cooper, and Robert Schrieffer in the late 1950s, is the most clever piece of cheating in physics. The electrons do not become bosons. They cannot, but they pair up. Two electrons, with opposite spins and opposite momenta, find each other and form a pair. The pair, as a single object, has spin 0. The pair, made of two fermions, behaves like one boson. Two antisocial particles joined together, with their fermionness cancelling out, dancing as a single bosonic entity. We call these Cooper pairs. And once the electrons form Cooper pairs, the Cooper pairs are allowed to do the bosonic trick. Billions of pairs, all settling into the same shared quantum state, all flowing together coherently, no friction, no resistance. That is superconductivity. The pairing is held together by an indirect attraction.